see about. I guess let's just start. So welcome back. This is somewhat arbitrary called Cohomology 2. And what I'd like to do is continue briefly with the weekly quasi-coherent modules and what you can do with them, and then show some like general theorems, and then make this computation for higher cohomology of affine schemes. And yeah, it's more or less it. So what you usually have as operations between category of quasi-coherent modules is pull back and push forward at least. And there exist similar operations, and I will use the same notation as you classically use for pull back and push forward, but they behave a bit different than usual. So, definition, we have some general map between types. That's the Y. Then, I mean, one I kind of implicitly already defined by saying something is functorial for cohomology, but yeah, let's look at that more precisely. So if I have something over here, I can pull it back, and maybe let's just talk about abelian groups. I mean, later we most of the time use modules when we apply something like this, but that's just forgetting some of the structure. And then we can just directly define upper star at some value x over here is, and that's just application. And that's what we call pullback of something. And if you think of it, about this as a bundle of groups, it's very visually the pullback. So the other direction works about as nicely. So if we have some n on x, some dependent abelian group, then we can push it forward. Lower star and y. And there you just take a pi over the fibers of your morphism. So this kind of appears sometimes. And I mean, you also have canonical maps. So from, to use n here, actually. So you have something from m into this one, into the pullback, and from n into the push forward. So there you can take like constant maps, and there you just pull back your section as well. Okay, so, but it's important to keep in mind that this is not like what you know from algebraic geometry textbooks. So this here is not like classical notion. And one example is that if you do it like this, upper star is exact. And I mean, usually for quasi-coherent modules, you should have some tensor product on affine schemes. And you should be able to decide if a morphism is flat, and not every morphism is flat by looking at what happens on lots of examples. And yeah, that's different here because we just do something different. If you think about it, we now have a bundle of modules over our spaces, which also are not like fiber-wise constant sheets or something like this. So they are just different objects a priori. Then
I think I'm a bit confused.
Yeah.
I mean, so in this setup, your modules go to, I mean, your functions go to the abelian groups. So you have not, I mean, the Z modules.
Yeah.
But I mean, but there you just take, I mean, there F upper star Z modules is exact. I mean, it's just because they do not have the tensor. I mean,
yeah, just I mean, basically you tensor, and that's something.
No, you don't. When you have models of abelian groups,
when you would take a module. I mean, maybe the defect is also that we just do nothing except this if we have a bundle of R modules.
Yes, there I would understand your comment, but not in this setting where you just go to abelian groups.
Okay.
That classically,
maybe because we don't need that. So let's make it more meaningful by saying like this. Yeah, okay. So maybe it's better to, at least for this column, to set it like this. Yeah. And what is interesting, if you do it like this, then this also kind of non-trivial is that, at least for the push forward, these are WQC modules. And I mean, what you need is that this for something WQC is WQC again. So the theorem you need is, which is not hard or something, is that scheme index products over WQC modules are WQC modules again. You get this. Okay, so now something which is kind of just abstract quantity type theory. I mean, this is also in some way is maybe that's a lemma. If so, I had this thing here as like a warning or an indication that something interesting is going on. And you also kind of have a reverse direction. So if enough cohomology vanishes, then you can commute these things. Then you have the equalities. And what you can do is this. So if you know for some type and some coefficient, if you know that this vanishes for all indices below n, then you can commute de-looping with exponentials like this. Because it's A on the outside and on the inside. This. And yeah, where this comes from is there's some uniqueness principle of unmapped plane spaces. So these vanishing cohomology groups give you enough connectedness. And for example, if you have a one-step de-looping and you have some space which is pointed and its loops are a given group, and you also know, like, you already know it's a one type, and if you also know it's connected, then it's already unique. And there's something similar for higher levels, and that's where this comes from. Okay, and this is kind of nice because it gives you a way of at least computing, showing that something is cohomologically trivial. But you also get a nice morphism. That's what I want to use later at some point, or at least point out, because it's kind of nice. So if you have some map and cohomology on fibers of this map vanishes, so in our case, I mean, that would be the case for some map where the fibers are fine, for example, which does happen. Then, so if you know HL of the fibers of F with coefficients in some pulled back M, so let's say you have M is some coefficient, and you restrict it to some fiber. So if you say Pi1 is like the inclusion from the fiber into the space, then if this is 0, like same condition as above, for everything below L, then you get almost just by using that more abstract thing that Hn of X with coefficients in M is the same as Hn of Y with coefficients with the push forward of M. This is really just type theory and using those things. So, okay. So this is actually one that I didn't remember from algebraic geometry. Maybe you do, I don't know. So does something like this hold?
Yeah, I mean, in general, you have to spectral sequence. I mean,
yeah,
and
I mean,
and the cohomology of the fibers is, yeah, I mean, you have to express it in high direct.
Yeah. So if you take the spectral sequence and plug in 0 for the fibers, you get this, I guess.
Yeah, I mean, if you look at Hartshorn, I mean, he tries to avoid spectral sequences, and so he formulated this for affine morphism.
Okay,
so then, but you have a statement, yes.
Yeah. Yeah, I mean, I haven't actually looked if you can like apply the spectral sequence, their spectral sequence within hot to our stuff. Maybe that
so yeah.
works. Yeah. Yeah. And then you
but I think this is a nicer formulation, because here you have really something that looks like a set theoretic fiber. And you do not have to talk about higher direct images.
Yeah. Yeah. I mean, it's nice that it's so simple in this case. Yeah. Okay. So there are two other like general theorems about cohomology I'd like to mention, and I briefly go back to homotopy type theory to like get the tools working in the background. So from hot, we can use the following facts, which are in the hot book. So if you have just some pointed map, indicate like pointed maps with a dot, and F, let's say, is the fiber of F. And because we have pointed things, we can talk of the fiber, because we know which point. And the fiber you can just write down directly in hot as the sigma type of all things that are mapped to the point over here by F, so with some equality. And that gives you the right notion of homotopy fiber. Or, I mean, you can say more abstractly, like this and also forget about the points here and say this is a pullback. And you can define pullbacks in homotopy type theory in a kind of easy, nice way, and those will be homotopy pullbacks, and you can show usual categorical lemmas about them. And proving them is not too hard. It's like reasoning in a 2-1 category, let's say. So this is nice, well, works nicely. And yeah, in this situation, then there is a long exact sequence of homotopy groups. So, yeah, so I look at the indices. Yeah. So you have pi k of f, which I haven't talked about, but homotopy groups in what you can just define for pointer type in general as loop space k times, and then truncating. It will give you the right homotopy group, and here you just apply pi to the sequence of pointed maps, pi k, and so it's x, it's y, and if you go up, the index increases. So here you have pi k plus 1, and the spaces are the same like in rows. So this continues here, and it's continuous also downward like this. And here the indices decrease. And this is very useful classically to make computations. So what homotopy groups of spheres or a Hopf vibration or whatever. So there are lots of examples using this, and it's also not too hard to prove in HUD. So you can start with some abstract pullback reasoning, at least to understand what you should do, and then you can make actual computations and show this is exact. I mean, this is a bit of a lie because it kind of here for high indices is a long exact sequence of abelian groups, and further down in the end it will become just groups and then just pointed sets for pi 0. But let's forget about the special cases because they won't appear for us when we use this to reason about cohomology. So what is kind of nice is that we can reuse this to get theorems about cohomology. Yeah, so one example which is very useful is the long exact sequence for short exact sequences of coefficients. So if you have just some arbitrary type and coefficients like this, such that you have a pointwise short exact sequence, and so when I say this sequence is exact, or you have a sequence, it means pointwise for every little x, you have a map between the modules. So everything is just pointwise. And turns out that also exactness pointwise is the right notion, which turns this into an abelian category. And yeah, what you get in this situation is the long exact sequence of cohomology group. There is a long exact sequence, a lot like this one over there, but with indices flipped. So what you get is you have some HK X. So this is the covariant. in the coefficients. And now the index upwards decreases. What we show you why. And the index downwards increases. Okay, where do I put it? Right here. Okay, so yeah, so some proof sketch, I would say. So first, what you have to note is that cohomology groups, as we defined them, are homotopy groups. So this is very important, like for all these abstract computations. So maybe let's do it once in detail. So if you have, just some arbitrary cohomology group, then by definition, let's expand it, it's this. And since we know that loop spaces cancel with delooping, we can insert a case loop space for some type inside. It doesn't change because you have some equivalence between this part and this part. So nothing happens. And I mean, at this point, it could actually make sense for k, which is an integer, but later on, it will only make sense for any natural k. So it's a natural number. And what we can do now is this thing I also noted before lunch. Ah, yeah, there it is. That you can switch omega with function types, which also works dependently. So I can just put it in the front and this thing. And then I see it's a homotopy group by this definition. So it's pi k of all of this. And yeah, I can do this for an arbitrary case. So I can view one fixed cohomology group, one Hn, as a pi k for a k that I'm allowed to choose. And I know it's always an abelian group. This is why this special case stuff here vanishes. Is not of concern to us when we apply this to cohomology. Okay, so did I want to say something? Ah, yeah, okay. I mean, to prove this using this, you still have to know that a short exact sequence of abelian groups gives you a fiber sequence of Eilenberg plane spaces. So, I mean, that's something you have for arbitrary much delooping. And you can also home into it and it stays a fiber sequence. So the other thing this is the general thing that you need. And the other thing is that let's just take this sequence over here. So if you take some random Algebraic McLean level, so X n, and we choose McLean. Then this is a perfect or so it's anyway. And yeah, so these two things together mean we can apply this a bit in a weird way because we have to apply it, I think, countably often and do some identifications. So it's a bit weird. And I mean, due to this, you can see that the indices are shifted around because if you increase this one, you have to subtract one of this here to still get a cohomology group back. So it's kind of why the order is switched around. Yeah, but I think I don't want to say more about this theorem. So. No, let me look at the time. Yeah. So, yeah. Okay. Yeah. So maybe let's do this one first. So yeah. Sorry for just stating abstract theorems, but it's kind of the order in which we use it. And yeah, I don't know if examples help you in the beginning to motivate doing this, because I kind of guess you have seen that this is something that is proven in some course, or I guess it's by itself motivated, hopefully. Okay, so let's make some space. And yeah, I mean, I only kind of briefly say what these abstract theorems are. The next one, the Miami-Torres sequences, are also something that works very abstractly. And maybe it's a bit surprising that if you want to go to check cohomology, it gets more complicated. And the theorems we have work only in something more restricted, like a more restricted setup. So, and also only for WQC modules. And this is also something you keep in mind, like these very abstract things, they work in general. And sometimes you really want to only look at cohomology with coefficients in some group that might not even be abelian if you only look at H1. So, and like this long exact sequence to some degree, of course, and the Miami-Torres still give you something at least. Okay, so this is my Torres sequence. So it's kind of in the other argument of cohomology, and specifically if you have a push out. So let X, let's just say it like this. So let this be just a diagram of types. And more specifically, a push out. The push out of types. And let's give some names. So this is F, G, H, A. Then and we need one coefficient on X. So, I mean, one case where you typically apply this is when you have a cover with two open parts, say. So you have a scheme here which is covered by two opens, and then this is the intersection, and you have a push out, and then you just restrict your coefficients to the parts in the intersection. So that's the coefficient A. Values in abelian groups. Then there is a long exact sequence which looks like this. So, what does it look like? You have union here, X, and your coefficient. And then you have the product of what's going on here. Perfect coefficients. And usually people tend to write this as a direct sum. What's the same in groups here? And here you have the intersection, and you also have a description of this map, like it's a difference map. So you pull back and do some difference. So I guess one can write this like this. It's sometimes important that you have a complete description. And here you need to make a choice and select twice. And yeah, it continues in the usual way. So you have hn plus 1 of x in A here. And this one of the same stuff. And I mean, one reasonable way you can apply this is, for example, when you have a scheme which happens to be covered by two affine things, like A2 without 0. And then if you already know cohomology vanishes on affine things, then you can easily compute the H1. Maybe you should actually write it down so you see at least one example.
Yeah, to have a second proof that H2 without logarithm is not
affine. Yeah. So H2 without 0 is the union of dx and dy. So if you view this as subsets of A2, you have the non-zeros of x, so everything except the y-axis and everything except the x-axis. And the union is this. And these are affine schemes. So, I mean, this is spec Rx, Y, localized at X, and so on. So, actually already with what we have seen earlier today, you can compute. So H minus 1 isn't a thing. So this sequence starts with H0 of A2. Let's say we use coefficients in R everywhere. So you have H0 here, so I'm just copying this line. So let's just call this dx for gravity. And y coefficients in R. I'm running out of space and can't do it in the nicest possible way, sorry. So I still have an H0 here of the intersection which is EXY. And here's an H1, which would be H1 coefficients in R we might be interested in. And after that, we only have a 0, because we will take H1 of the fine things. And we already saw earlier that 0, so we're good. And we know the sequence is exact. So we know, like, this map is surjective. Like, so here the kernel is everything. So the image has to be everything. So yeah, now we could compute. Does it actually work? Yeah. I guess it's an exercise. Let's not start it too long. But I think it actually works and gives you the answer that does it have a number. But it should take we don't need it now. Okay. So and the rest of the week, I guess. Okay. Now I'm a bit puzzled. I thought it was easy, but I just don't remember. I mean, yeah, in at least kind of compute what you have. So, it takes a while, I guess, to see exactly what's going on. But I mean, these H0 things are all fine except the first one, so you know what the modules are and you know what the maps are. So this is this difference map, and then it should work to compute it and give you some reasonable answer, which is that H1 is not trivial. Like, I mean, it doesn't have to be, because not everything which is not affine has some non-vanishing H1 for this particular coefficient. I mean, it has a non-vanishing H1 for some coefficient, but yeah, it doesn't have to be this one. Okay, so yeah, so I want to say something about the proof of Majoritoris. In the end, it's applying this exact sequence again. And the question is more, how do you get this fiber sequence that matches this one? And the answer is you take this push out and home out of it into your coefficient, and this turns it into a pullback. And then you have to do some clever pullback pasting, and then you get this sequence. If you want to look it up, it's written down in our draft on check cohomology. That's like in the beginning. And, yeah. It's quite abstract. So, not checking. Okay, I guess I erased that one. What you also can compute with the Majoritoris sequence is that if instead of the line with the double origin, so you could also look what happens with the line with double origin, it's push out. You can also look at the plane with double origin, and that turned out to have a non-trivial H2, which I found also kind of nice. And you can just compute it with the Majoritoris sequence. And yeah, okay, so, yeah, now I want to get back to this theory, which tells us that the higher homology of an affine scheme vanishes. If you have a coefficient, which is a WQC module. Okay, so it's done by induction. And the case n equals 1, we already knew. And the case n greater 1 was as follows. So you kind of do the same again. So you note you want to show like this type here is connected. So you want to show some cohomology class, some type of this form is connected. This need to show and we do the same again. We ask the risky local choice for trivialization in a cover. So local choice gives us a cover. Let's just call it UI. Some finite index segment I and SI trivializations. Like this. And it's a bit about analyzing, like, yeah. Okay, I make it different because just this way. So you can define the set of indices where some specific X is in the cover. And this is also like the fiber, so you can view this cover as a map into X. And what I define here, the IX is the fiber of this map. So it's the I in I such that UI of X. And this is affine because it's a sigma over affine things. So we know our cover is given by this D of F. So it's affine. I mean, the general open is not affine, so it's very important here that we are in an affine scheme where we know this cover will be affine. So we have a sigma over affine types. So standard finite types are also always affine. So the whole thing is affine.
I don't understand your comment. You said that it was important that we are an affine scheme. But I mean, when you have a very local choice, I mean, you can assume that the small sets, I mean, they are not the S, but they are, you can choose them to be affine.
I guess you can also do a separate. I'm not sure. I mean, in a general scheme, if you use the risky local choice, it's not clear that you're. Okay.
No, but you can localize further, yeah. So,
all right, yeah. It's not a basic open, but it's no.
I mean, you have a cover by opens.
Yeah.
But they are schemes. The open subset of schemes.
Yeah.
So you can cover these by affines. And then you can refine your cover so that you
well,
have a cover by affines.
I mean, I think, yeah, I mean, that's a good question, but I think the answer is at least not clearly yes, if you can cover a scheme a general one in a way such that, like with affine opens, in a way such that the fibers are affine. At least I wouldn't know if that's true. I mean, it's certainly a large class of schemes, but I don't know if it's all schemes.
Yeah, but why do you want the? I mean, here you have the UI. You said the UI are affine.
Yeah. I mean, that's what I use as an argument to show this is affine.
Yes.
This is the important part. I mean, yeah, okay.
Yeah,
the UI are affine more generally. That's great. No, I mean, if I have an open subset of which happens to be affine of a scheme, then I don't know if the proposition is affine, or do I? I don't get it. So.
And if the subset is of the form DF, then the proposition will be affine.
Yeah, sure. But I mean, in general, if I have an open subset of a scheme, the proposition that something is in this open subset, I wouldn't know why it should be affine.
Yeah, okay.
Maybe it is, but I wouldn't know why. Oh. Should I write down the question for everyone? I mean, if you have U open, and X just some scheme, but I don't. Yeah, I mean, that's clearly no. Yeah. I mean, there you have examples where this proposition X, or maybe let's write it like this, that some point is in this, need not be affine, or let's say it's not affine internal. And an example is like A2 without 0. And this is certainly no. And I mean, if you say I have an affine cover of my scheme, I don't know if it changes something if you know that if you sigma this one up, it's affine. This doesn't tell you that these are affine.
No, you can. I mean, you can still refine your cover, but I mean, maybe when we start with a non-separable scheme, it's just remarked. I mean,
what is separated scheme?
No, non-separated scheme. Maybe it will never work.
Yeah.
For some.
Yeah.
Yeah. Okay.
But yeah, for an affine scheme, and I guess for a separated scheme in general, this works, that you get that these fibers are affine. Okay. So how do we use this? Let me look where I should start. Yeah, I mean, the point why this is important is when you move from this thing, maybe just this. If you move from this thing to that thing, then and call this delta x, then we know delta x of pi x is 0. So it becomes trivial when you map over here. Why? Because for each element of this type, you know it's trivial. So because if I have an element of this type, I can use the triviality proof I have on this cover. I get a trivialization. So maybe I should write this down. Yeah, so this P is given by, so P of some witness of this, like I, and let's call this Q. You take Q and apply it here. So then you know you can kind of use this equality. So I'm doing a bit of syntax overloading, and you get that pi is trivial. So it's like this. So I mean, Q is silently in here. Maybe I'll put it like this. So that's how you get the trivialization. So, but I mean, in other words, you could say if you pull back your chi up here, so that's maybe the more classical, not so pointwise way, it becomes trivial by, yeah, that's how this cover was constructed. We asked Zariski law controls for cover with this property. Yeah, so, but how do we see this is enough? So this was really the hard part of the trick that I didn't expect. So this is a cool idea of David. And what he did is, you first note that you can factor delta over this space. And you can do it by using the universal property of this Algebraic plane space, which I didn't go into really. So, I mean, when you loop often enough, these things will become the same. At least if you loop n times, then you will have the same groups. Again, by this one thing that you can commute loops with function thing. And yeah, so you can do it in a way such that this becomes delta x. And what you can do now is say, okay, chi becomes 0 here. We want to actually know that it already was 0 here. And to see this, we want to know that this is an embedding. So let's call this map maybe F. Pi as an element in here. So you can also move it over here. Is 0 if F is embedding, which means it's an equivalence on identity types. And because our spaces are connected, or at least this one, we only have to check it for one point. So we can loop the whole thing. I should use one dot. So this last thing is equivalent to, because of the specific situation with connectedness and so on, to loop at, and now let me write it down again. Ix n minus 1, then so x n minus 1 to ix is equivalence. And I mean, this is what makes the argument inductive as a whole. And I mean, now you can kind of use what I wrote down earlier. So, yeah, so I want to write it down carefully. So this is not entirely true because you have to check what maps you actually used and It's actually a bit more work what you have to do here. But essentially this follows now from induction hypothesis for L smaller than n0, because this one gives you that Hn of Ix, HL of Ix, coefficients in Mx is 0. So by induction hypothesis, we know this for affine schemes. This one is affine. So good. And then we kind of know we can commute these two. I mean, we have to check for which map and so on. So if you look up the actual written down proof, this is just the middle and then it goes on, but maybe for presentation, this is not so important, but consider that. So this is what makes it work, that you can get out in this way. Okay. Yeah. So that is already over, but I want to at least mention some cool example that Hugo computed. It has an equation, so I should carefully, Hugo computed with an equation. So it's more like a theory, just an example, I would say. So, and you can tell that now it's really algebraic geometry. You have to say characteristic is not 2 or 3. So, implication, so to say. Then, if you consider like a general cubic, I guess might be the right term. I guess Mike will tell me if I'm wrong. So be set with 3. So this is a homogeneous polynomial, and A and B are parameters, and we view it as a subset of projective planes. And it's even pointed by infinity. So Ry actually, because what? This is true. I'm not sure I get it. No, it's 1 in the middle. So y doesn't appear alone. So yeah, if you put in this infinity, pointed this. So we have at least one point, which is good. And you can define what is called the discriminant. And
so I mean, it's a general cubic with a point.
Okay.
I mean, because if you have no rational point, then you cannot bring it into a Weierstrass form.
Okay.
Mm-hmm. I mean, like
general cubic.
Come up or the previous.
Okay. Yeah. Okay. It's some cubic with a point, and if we ask this to be non-zero, we can say it's a Weierstrass curve.
Yeah, it's smooth.
Yeah. So it's something Hugo proved. With this, it's smooth, and in general, you can compute using the Malvitore sequence that let's call this ELB. That ELB, the coefficients in R is R. So global sections are limited as with projective space, which we haven't mentioned, I guess. And H1 is also R, so of rank 1, as it should be. And yeah, for the proof, you use Meyer-Torres, and then you calculate with modules, and it's good. Okay, thank you. For questions or comments?
Well, maybe I missed this. I mean, luckily that I missed it. So in your Meyer-Torres sequence.
Yeah.
So can you get it by, from the short exact sequence from a short exact sequence of modules?
Where short exact sequence?
Where you have something like A goes to
okay.
A
So
upper star A, well, push forward plus K upper star A also push forward.
I don't know. I really only know this one way to get it, but
okay.
I don't see how it.
Okay.
I mean, in the end, you have one fiber square.
Yeah.
And I guess you can interpret what you see as a short exact sequence of modules somehow, maybe.
Yeah, yeah. I mean,
but then it's not on the same space, really. So kind of weird, I guess. Yeah.
Well, maybe it's what I'm saying is the same as that the check complex is cyclic. I mean, when you do the sheaf check complex.
I don't know how that's the same, but
when we have a cover of two open subsets.
Yeah, in some special case. I mean, this is a general push out, and yeah. I mean, you have, yeah, you have the check situation. It's a special case of check for the situation where the check applies, where it's like a cover of subsets on a scheme, and at least the check we know here in this context. You need a lot more conditions. So. Okay. Yeah. We start again at 3:30.
Yeah, stable. Okay.